Where z-transforms really shine is in transfer functions. So, as an example, suppose you had a system defined by a difference equation, and you want to analyze this using the z-transform. Well, just as you can perform a lot of operations to equations as long as they're performed equally to both sides of the equation, you can also take the z-transform of both sides of an equation. We take the z-transform of the left side of the equation first, yielding y of z. Put that in black. Okay, on the right hand side, we take the z-transform of that expression. And due to linearity, we know that we get 0.5 y z, but it has a delay, so that gives us a z to the negative 1 out front, plus 0.3 times the z-transform of x. We don't know what x is, but we know it has a z-transform of x of z. And there we go. We can now solve this equation for the ratio of y over x. Why, you may ask? Hopefully this will be clear in just a moment. So we have y over x of z is equal to 0.3, in this case, 1 minus 0.5 times z to the negative 1. So this is much like the frequency response we saw before. Remember, when you convolve two things, it's like multiplying in the frequency domain. So if we define this term now as h of z, then we could also write it as y of z is equal to x of z times h of z. So we can compute the output in terms of the z-transform just as we did before in terms of the dtft. In general, if we're given a difference equation of the form k equals 0 to n of aky n minus k is equal to, same thing on the right, 0 to m bk x n minus k, then we can take the z-transform of each side and the z-transform of the left side. Due to linearity again, we'll get a sum. The ak's come through, and we'll get z to the negative k times y z. And on the right hand side, same thing, a sum from 0 to m bk z to the negative k x of z. Solving for h of z, gives us now a sum, because we can factor out our z-transforms from this. They're not functions of k anymore. Sum from k equals 0 to m bk z to the minus k, and the sum from k equals 0 to n of ak z to the minus k. So, something very important to note. Here we have the definition of h of z, and if it helps you remember, the x is on the bottom because it has two legs, and it has to hold up this big stack. It has to hold a y above it. So the x is on the bottom, sitting there with his legs out and his arms up, holding up the y. So that maybe will help you. It's a stupid little example, but it'll help you remember how that's defined. Over here, on the other hand, the x coefficients go on top. And the y coefficients are on the bottom. I don't have a pretty little way to remember that, only that it's opposite of what it is over there. And that's just the fact that we're doing a cross multiplication to get back to our original multiplication, our original equation. Okay, so that's the Z transform. And not a surprise, we've already done this before, but if we were to take this and evaluate our transfer function, we would get, well, the frequency response, the sum over k of bk e to negative j omega k over the sum of the ak's times e to negative j omega k. So there's a quick way of getting from the actual signal or the coefficients, whatever you've got, to this type of relationship. The first thing you notice is if you're given a difference equation, all you have to do is pick off the coefficients, and according to the index k, you put a z to the minus k. That's it. Another way, if we come back here and look at what we did earlier, we can go from step 1 here to step 2 there by the following rules. Anytime you see a little y, replace it with a big Y. Same with the x's. Anytime you see a coefficient, a multiplier, it stays the same. And anytime you have a delay like n minus 1 or n minus 2, take out whatever the delay is and put a z to that power out front. And so, for example, here we went 0.5 yn minus 1, that becomes 0.5 yz, capital Y, times z to the minus 1. So those are the simple rules, and you can find the Z transform of any difference equation or related type function, and using that we can find the transfer function. Now, before I talked about how multiplying two sequences in the Z domain is computationally equivalent to actually performing the convolution. And that's true. If you want to multiply two polynomials in MATLAB, you use CONV, the convolution function. But once we get to this Z transform form where we have a ratio, now things start to look differently. And we're going to spend a little bit of time in the next lectures looking about how to invert the Z transform and evaluate the outputs of a system based on the transfer function.